Welcome back, and we're just going to look at the last little bit of atomic structure for this bit, which is isotopes. And you should already be familiar with isotopes. We're just going to have a quick review of them. So remember, we've defined our atomic number as being Z, which is equal to the number of protons. And then we said that our mass number A was equal to the number of nucleons, or the protons plus neutrons. Okay, so now what we're going to talk about is what happens if we change this one. Okay, so remembering that this one doesn't change. If we change the number of protons, we change the element. So now we're going to talk about different forms of a single element. So isotopes have the same atomic number but a different mass number. And this different mass number arises because they have a different number of neutrons. Okay, so, and this is set. Some elements we find isotopes of, and there are elements of most isotopes. There are isotopes of most elements. However, the type of isotope they form tends to be set. So for carbon, we get 3 isotopes. One is carbon-12, which is the most common. It forms up about 98.9% of all carbon atoms. But there is a small amount of carbon-13, about 1.1%, and an even smaller amount of carbon-14. Okay, so remembering that when we write the symbol for an atom, we put its symbol and then its mass number, its atomic number, which for carbon is going to be 6, and then in the case of carbon-14, its mass number is 12. And when we write this, when we identify what the isotopes are, we usually just change the mass number up on the top. Just note, sometimes you will see them written like this on the right-hand side. By convention in Australia, we write them on the left-hand side. This is actually an American notation form, and we don't tend to use that. So if we have a look at this, we can also see chlorine has isotopes. Okay, chlorine has 2 isotopes. One is chlorine-35 and one is chlorine-37. So chlorine-35 has 18 neutrons, with it being the atomic number 17, whereas chlorine-37 has 20 neutrons. So you can see that they don't always equal the same thing, and that this makes them just that little bit heavier. So if we look at silver, okay, we can see here we have silver 107 and silver 109. So if we have a look, we can see that the atomic number of silver is 47, because this is given here. This is Z, which is equal to the number of protons. Okay, because it is neutral, it will have electrons will be equal to the number of protons because it is a neutral atom. Okay, so that's going to be 47 electrons. And then our number of neutrons, okay, is going to be equal to our mass number minus our proton number, which in this case is going to be 47, which is going to leave us with 60. So that's going to be 60 neutrons, whereas in silver 109, if we look at this one, it's going to have exactly the same number of protons, exactly the same number of electrons, but now we've got 109 minus 47, which is going to equal just that little bit more. Okay, so we're going to have 62 instead of 60 as our number of neutrons, but in all other respects they're going to be exactly the same. So when we talk about them being exactly the same, we're actually talking about their physical and chemical properties. Because they have the same electron arrangement, their chemical properties are going to be exactly the same. So they will react with things in the same way. We won't be able to tell them apart chemically. Physical properties depend on the nucleus. So in this case, they're going to be a little bit different. Okay, so they will weigh a little bit more, and their density will be slightly different. So they have exactly the same number of electrons, okay, and they have a different nuclei structure. Okay, so this means that we get that mass structure, which is different. So here's a couple for you to try. I want you to pause the video and then come back and see how you went. Hopefully this is what you came up with. You used your periodic table. Because it's asked for the atomic notation, this is also the nuclide symbol notation. Okay, so hopefully you used your periodic table and you got these right. So this is one we did just before. So atomic number 47, 109, which is our mass number in the top left. Chlorine, atomic number 17, mass number 37 in the top left. Mercury, which is the only one that we hadn't covered in this PowerPoint up until now, is an atomic number of 80, found in the D block transition metals, and that gives us a mass number of 202. So these are a couple of things that you need to remember when it comes to isotopes and ions. We're going to talk about ions again a little bit more, but you should be familiar with them from your previous studies. Okay, so isotopes have different atomic structures but react the same way chemically. Okay, so they can still form ions and things like that, but they will react exactly the same way chemically. It's very difficult for us to determine the difference between isotopes. Ions, however, differ only in the number of electrons. So they don't differ in the number of neutrons, and they certainly don't differ in the number of protons. That is where we add or remove electrons. So it's very important for you to be able to define the difference between an isotope and an ion. Okay, so the difference in electron configuration, so the difference in the valence electrons of ions, means they have different chemical properties than the neutral atom. Okay, so remember, ions gain or lose electrons to become more stable, so they certainly behave differently to the neutral atom before they've done that. Okay, so ions will have the same nucleus structure, but different electron configuration, so their chemical reactivity is different, whereas isotopes have the same electron configuration, but the same so it has the same chemical properties, but differs slightly in its physical properties because of the different structure of its nucleus. And that is pretty much what we need to know. It is worth being familiar with a couple of radioisotopes. These are isotopes that give off radiation as they decay of different types, and we often use them for medical purposes. So carbon-14 we use for radiocarbon dating. Iodine-131 we use for medical imaging, same with iodine-125. Thyroid mostly for 131, and prostate and brain tumours for 125, also because it's taken up by the thyroid gland. Then we use cobalt-60 for a number of purposes, including radiotherapy, but also sterilizing food and spices because they're seeds. We use that to sterilize them so they don't germinate. And then these ones here are used in smoke detectors and also for some biological processes. You don't need to know these in detail, but you do need to realize that they may turn up as examples and things, and just not to freak out about them. That usually that question is asking about isotopes, and therefore will have just the same sort of things associated with it as normal. So these are a couple of short videos for you to watch if you need to cover this anymore, but other than that, I'll see you in class.